All right, let's jump into this deep dive on heat pipe nuclear fuel assemblies. This technical document, wow, it's really something. We're talking about reactors that basically, like, cool themselves, right?
Yeah, that's the idea behind HPNFA. It's pretty amazing stuff.
Yeah, and this is huge when you think about SMRs or even space reactors, right?
Yeah.
Like getting rid of those giant pumps and all the piping.
Absolutely. Those pumps and pipes, they can be a real headache in terms of safety and maintenance. HPNFA kind of sidesteps all that.
Okay, so how does this thing actually work?
Yeah.
I mean, we're talking about heat traveling without pumps,
yeah.
right? The document mentions this bundle of fuel rods, like in a regular reactor, but there's also this wick structure thing, all sealed up in a metal casing.
Right. So think of it like this. You've got your fuel rods. They're generating heat from fission, just like in a conventional reactor. But instead of water or some other coolant being pumped through, we're using a liquid metal, often sodium, which has awesome heat conductivity.
Sodium? Like table salt sodium?
Well, not exactly table salt, but yeah, sodium, it's great at transferring heat. And the wick, that's the key. It's this porous metal mesh that surrounds the fuel rods. As the sodium near the rods heats up, it vaporizes, and that vapor carries the heat up to the cooler top of the assembly.
So it's like a little self-contained weather system inside the reactor.
Kinda, yeah. The hot vapor rises, and then at the top, it condenses back into liquid, releasing that heat. And the wick, because of capillary action, pulls the cooled liquid sodium back down to the bottom where it can absorb more heat. It's a continuous cycle, all driven by those phase changes.
That's wild. And this whole thing, the wick drawing the liquid down, it even works in zero gravity.
Yeah, that's one of the things that makes it so cool. Literally, it opens up possibilities for space reactors, like powering a lunar base or something. No pumps needed, just physics doing its thing.
That's, yeah, mind-blowing to think about. But okay, let's come back down to Earth for a minute. What are the real-world benefits of HPNFA here and now?
Well, I think the biggest one is safety. By getting rid of pumps and all those pipes, you're basically eliminating a lot of potential failure points.
Yeah.
Less chance of leaks, less chance of mechanical problems. It's inherently a more resilient system.
So simpler means safer in this case.
Exactly. And it's not just about safety. Because the system can operate at higher temperatures, it also opens the door to using more efficient power conversion systems.
Yeah, the document mentions these supercritical CO2 cycles. I don't fully get it, but it sounds like they're way more efficient than those giant steam turbines they use now.
Right. Supercritical CO2 is like the next generation of power conversion tech. HPNFA is a perfect match for it. We're talking about potentially squeezing way more electricity out of the same amount of nuclear fuel.
That's impressive. But, I mean, there's got to be a catch, right? The document does mention the cost. Apparently, these HPNFAs are a lot more expensive to make than regular fuel assemblies. What's driving that?
Well, a few things. First, you've got the materials themselves. We're talking about specialized alloys for the casing, high-performance wick structures, and liquid metals, which are not exactly cheap to handle.
So the ingredients are pricier. What about actually making the thing?
Manufacturing is definitely more complex. We're talking about precise engineering, airtight seals, perfectly integrated components. All of that adds to the cost. And right now, we're still in the early stages, so we haven't achieved economies of scale yet.
But, I mean, the document does hint that, you know, if we start mass producing these things, maybe using some fancy new manufacturing techniques like 3D printing or something, the price could come down significantly.
Definitely. There's a lot of room for innovation and optimization. And if space exploration starts using this tech, that could also drive down the cost because, you know, those guys have deep pockets.
All right, so we've covered the basics, how it works, safety, efficiency, and the cost issue. Where do we go from here? What else is there to unpack about this HPNFA thing?
Well, now that we've got the big picture, I think it's time to dive a little deeper into the nitty-gritty of the materials science and engineering that make this all possible. It gets pretty fascinating, trust me.
All right, let's do it. I'm ready to get technical.
Okay, so you're ready to get into the materials. Before we do that, you know, we were talking about space reactors earlier, and it just blows my mind that this could actually work, you know, up there.
Yeah, it's pretty wild. The document kind of glosses over it, but I mean, powering a lunar base with HPNFA, that's straight out of science fiction.
Right. It really makes you think about the possibilities, even here on Earth, if it can handle that kind of environment.
Okay, so materials. When we talk about, like, the anatomy of an HPNFA, what are the main pieces we need to think about?
Well, you've got the fuel rods, of course. That's where the heat comes from. Then there's the wick structure, and the whole thing is encased in this outer shell. Each part has to be carefully chosen to make sure it all works right.
So, starting with the fuel rods, are they basically the same as what they use in regular reactors?
Yeah, pretty much. Usually it's uranium pellets or sometimes mixed oxide fuel. That's the stuff that actually undergoes fission, and releases all that energy.
Okay, so the fuel rods are the heat source.
Yeah.
And then we've got the wick, which we talked about a little earlier.
Yeah.
What's so special about the material they use for that?
The wick is like the heart of the whole passive cooling system. It needs to be really tough, and it has to be good at moving that liquid metal around.
The document mentions tungsten and also niobium. Why those metals specifically?
Well, for a few reasons. First, they're both refractory metals, which means they can handle crazy high temperatures without, melting or falling apart. That's pretty important inside a reactor.
Yeah, no kidding. But what about their ability to, actually move the liquid metal?
That comes down to their capillary action properties. They're really good at that, which is exactly what you need for the wick to draw the cooled liquid metal back down towards the fuel rods.
So choosing the right wick material is mission critical for the whole thing to work, right?
Absolutely. Get that wrong, and the whole system could fail.
Yeah.
And then there's the outer casing, the thing that holds it all together. It's basically a high-tech pressure cooker, right? It's got to contain the liquid metal, withstand all that heat and radiation, and absolutely no leaks allowed.
So we're not talking about your average everyday steel here.
Nope, definitely not. The document talks about using these super alloys like in Chemil 718 or even oxide dispersion strengthened steel. That stuff is seriously tough.
Okay, so we've got superheated fuel rods, a high-tech wick, and a super alloy pressure cooker to hold it all in. And then, of course, there's the liquid metal itself. What are the main contenders for that role?
Well, sodium is a popular choice, and lithium too. They're both fantastic at transferring heat, which is like the whole point of this system, right? To move that heat away from the fuel rods as efficiently as possible.
So we've got our lineup: fuel, wick, casing, liquid metal. Is it really that simple, though? I mean, the document mentions this cladding thing, too. What's that all about?
Ah, yeah, good catch. The cladding is like a protective layer around the fuel rods themselves. Don't forget those rods contain radioactive material, and we gotta make sure that stuff stays put.
So the cladding is kind of like a barrier to prevent any leaks of radioactive material, right?
Exactly. And it needs to be really, really resistant to corrosion and all that radiation. Silicon carbide SE is looking like a good candidate for this. It's a ceramic material, super tough, and it can handle the harsh environment inside the reactor.
Okay, so we've got all these special materials, each one chosen for its, superpowers, right?
Right.
But how does it all actually work together? We know it's this passive heat transfer cycle, but can you walk us through that step by step?
Sure. So it starts with the fuel rods. They're undergoing fission and generating a ton of heat. That heat transfers to the liquid metal, which is hanging out in the wick structure right around each fuel rod.
So the liquid metal is basically soaking up all that heat like a sponge. What happens next?
As it absorbs more and more heat, the liquid metal eventually reaches its boiling point. And when it boils, it turns into vapor, like steam. But this vapor is super hot, and it carries all that heat energy upwards.
Because hot stuff rises, right?
Yeah.
Like a convection current or something.
Exactly. It's all driven by that pressure difference between the hot zone down by the fuel rods and the cooler zone up top.
Okay, so the hot vapor goes up, then what?
Well, at the top of the assembly, there's a condenser section. That's where the vapor comes into contact with a heat exchanger. That could be part of a power conversion system, like those supercritical CO2 cycles we were talking about.
And when the vapor hits that cooler heat exchanger, it condenses back into a liquid, right? Like steam turning back into water.
Yep, you got it. So now we've got cool liquid metal up at the top. And that's where our wick structure comes back into play.
Time for the super sponge to work its magic.
Exactly. The wick, through capillary action, pulls that cooled liquid metal back down towards the hot fuel rods, where the whole cycle starts again. It's this beautiful, continuous loop, all driven by physics, no pumps or moving parts needed.
It's amazing, really, this simple concept, this heat pipe. It's like a little engine that could power, whole cities.
Mm-hmm.
But even with such a, elegant design, there's got to be some challenges, right? Making all this work reliably,
Oh, for sure. Like with any complex engineering system, there are always hurdles to overcome. And with HPNFA, one of the biggest ones is making sure all these materials can actually, last. We're talking about extreme temperatures, intense radiation, corrosive liquid metals. It's a pretty brutal environment.
So it's not just about finding materials that can handle the heat for a little while, but for years, decades even, right?
Yeah, exactly. That's where material science gets really important. Scientists and engineers are constantly working on developing better alloys, coatings, new ways to make these components more resistant to all that wear and tear.
So what are some of the material challenges that they're focused on? I mean, specifically.
One big one is corrosion. You got to prevent the cladding material, the stuff that's in direct contact with the liquid metal, from corroding. Even a tiny bit of corrosion could be bad news for the fuel rods.
So it's not just about keeping the liquid metal contained, it's about keeping it from, eating away at the fuel rods themselves.
Yeah, it's a two-way street. That's why they're looking into new cladding materials, like that silicon carbide we talked about, and also special coatings that can protect the metal. It's a tough challenge finding stuff that can withstand those corrosive liquid metals for a long time.
What about the wick? I imagine that keeping its porous structure and making sure that capillary action keeps working, that's got to be a challenge too, right?
Oh yeah, absolutely. The wick needs to keep pulling that liquid metal downwards even after years of being bombarded with radiation and heat. So finding materials that can handle all that without, falling apart or getting clogged up, that's essential. Those refractory metals like tungsten and niobium, they're really good at that.
It seems like material science is like the unsung hero of this whole HPNFA thing, right?
For sure. It's not just about cool concepts, it's about the materials that can actually make it a reality, but materials are only part of the story. We also need to think about the design and how these things are actually built.
What are some of the key things to keep in mind on the design front?
Well, you got to make sure the wick structure is integrated properly with the fuel rods and the casing so that the liquid metal flows evenly and there are no leaks. All the seals have to be absolutely airtight. It's like a high-stakes puzzle, where every piece has to fit perfectly.
And with all these complex parts and materials, I imagine it's not easy to actually manufacture these things.
You're telling me. Traditional manufacturing methods can be really tough and expensive for something this intricate. That's why a lot of people are excited about the potential of 3D printing.
Wait, 3D printing for nuclear reactor parts? That sounds kind of crazy.
It does, right. But think about it. If you could print those complex wick structures directly inside the casing, it would simplify the manufacturing process a ton, and it would give you much more precision and control, which could lead to better performance and lower costs.
So 3D printing could be a game changer. What else are researchers working on? I mean, what other challenges are they facing with this tech?
Well, there's the whole issue of what happens when the reactor shuts down or, if there's some kind of unexpected event. Even when the reactor's off, the fuel rods still generate some heat from radioactive decay.
Oh, right. I forgot about that. So even when the reactor isn't actively running, the HPNFA still needs to be able to handle that leftover heat, right?
Exactly. That's why you need to design in some safety features, like passive cooling mechanisms, things like natural convection loops, or emergency radiators. It's all about redundancy and making sure the system can handle whatever gets thrown at it.
Wow, it's amazing how every little detail matters with this technology. From the materials to the design to how it operates, it's all got to be carefully thought out.
Yeah, that's nuclear engineering for you. It's complex and challenging, but also incredibly rewarding. So are you ready to move on to the experimental phase? See how researchers are actually putting these HPNFAs to the test?
Absolutely. Let's see how this thing performs in the real world, or at least as close as we can get in the lab.
Okay, so we've talked a lot about the theory behind these heat pipe fuel assemblies, but I'm really curious to see how they actually perform out there in the real world, or at least as close to the real world as we can get in a lab.
Right. Well, that's where the experimental testing comes in. Researchers are putting these HPNFAs through some pretty rigorous tests to see how they hold up. So how does that work? I mean, they can't exactly build a full-scale reactor just for testing, right?
No, of course not. They use these scaled-down versions of the HPNFA, and they test them in these specialized facilities that can simulate the conditions inside a reactor.
But they're not using actual nuclear fuel for these tests, are they? That seems a little risky for a lab environment.
No, definitely not. Instead of using real nuclear fuel, they use these electrically heated rods to generate heat. It's basically like a mock reactor, so they can study how the HPNFA behaves without, having to deal with all the hazards of radioactive material.
Oh, that's smart. So they've got this mock reactor set up. What kind of tests are they running on these things?
Well, they're measuring a whole bunch of things. Temperatures at different points in the system, the pressure inside the heat pipe, the flow rate of the liquid metal, all that stuff. And they even use some pretty sophisticated imaging techniques to actually see the heat flow in action.
Wow, that's cool. It's like giving the HPNFA a full medical checkup, but with high-tech sensors instead of, stethoscope. So what are they looking for in these tests? What are the main things they're trying to figure out?
One of the big things is verifying that the whole heat transfer mechanism is working as it should. Making sure that the liquid metal is absorbing heat from the rods, vaporizing, traveling to the condenser, and then coming back down as cooled liquid, the whole cycle.
Basically, making sure the heat pipe is doing its job, moving that heat efficiently and reliably.
Exactly. And they're also keeping a close eye on the wick structure, making sure it's maintaining its capillary action over time so that liquid metal keeps flowing smoothly. That's super important for long-term performance.
Right, because if the wick gets clogged up or something, the whole system shuts down.
Mm.
And I imagine they're also monitoring the temperatures very carefully, right? Making sure nothing gets too hot and that the materials can handle it.
Absolutely. They're looking for any signs of, material degradation, corrosion, leakage, anything that could compromise the safety or the lifespan of the HPNFA. These tests are designed to be really tough, to push the technology to its limits.
Okay, so they're really putting these things through the ringer. But what about safety specifically? How do they know that these HPNFAs won't, pose a danger if something unexpected happens inside a real reactor?
Well, they simulate different accident scenarios, like what happens if there's a loss of coolant flow or if there's a sudden power surge. They want to see how the HPNFA responds under those kinds of extreme conditions.
So it's like they're trying to break the system on purpose, but in a controlled way to make sure it won't break in a real-life situation.
Yeah, that's a good way to put it. They're trying to understand its limitations, its weaknesses. And the good news is that the results so far have been very encouraging. The HPNFA has demonstrated some really impressive safety features. Even when things go wrong, it's very resilient.
That's great to hear. But even if it works perfectly and it's super safe, there's still the issue of cost, right? We talked about how these things are more expensive to make than traditional fuel assemblies. Are they doing anything to try and bring that cost down?
Oh, absolutely. Researchers are exploring all kinds of ways to make HPNFAs more affordable. One of the simplest ways is just to scale up production. Right now it's expensive because they're only making small numbers of them. But if they start mass producing these things, the cost per unit should come down significantly. It's just basic economics.
Right, so mass production could be key. What about the materials themselves? Any chance of finding, cheaper alternatives to some of those high-tech components?
Yeah, they're definitely looking into that too. They're experimenting with different materials for the wick structure, for example, trying to find something that performs as well as those expensive refractory metals, but costs less.
So it's all about finding that balance, right? Performance, durability, and affordability. It's like a three-way tug of war.
Exactly. And don't forget about those advanced manufacturing techniques, like 3D printing. If they can figure out how to print those complex components, that could be a real game changer in terms of cost and efficiency.
Yeah, 3D printing really seems like it has the potential to revolutionize a lot of industries, including nuclear.
No doubt. Well, it's been really fascinating talking about this with you. We've covered a lot of ground, from the basic principles of how these things work to the materials science, the engineering challenges, and even the economic considerations. It's a really exciting field with a lot of potential to change the way we think about nuclear power.
I agree. And it's not just about making nuclear power safer and more efficient. It's also about opening up new possibilities, like those space reactors we were talking about. Who knows what the future holds for HPNFA? It's a great example of how science and engineering can come together to solve some of our biggest challenges.
And for our listeners out there, keep those questions coming. The more we learn about these new technologies, the better equipped we'll be to make informed decisions about our energy future. So stay curious, and thanks for joining us on this deep dive.